Right now, 250 miles above your head, 6 people are living inside a structure that costs $8 million every single day just to keep running. That's not the construction cost. That's the daily operating expense. The International Space Station burns through more money in 24 hours than most Americans will earn in their entire lifetime. But here's what nobody talks about. Every single dollar is essential. Without it, the astronauts up there would be dead in minutes. Oxygen doesn't exist in space. The ISS has to create it from nothing. The system is called the Oxygen Generation Assembly. It uses electrolysis to split water molecules into hydrogen and oxygen. The oxygen gets pumped into the cabin. The hydrogen gets vented into space. This process runs continuously. Every breath an astronaut takes comes from water that was split apart by electricity generated by massive solar panels. The system operates 24 hours a day, 7 days a week. There are no breaks, no maintenance windows. Stop the oxygen generation and people die. But creating oxygen is just the beginning. The real challenge is removing carbon dioxide. Humans exhale CO2 with every breath. In a sealed environment, that CO2 builds up fast. Too much CO2 and you suffocate, even with plenty of oxygen around you. The symptoms start subtle. Headaches, confusion, drowsiness, then unconsciousness, then death. The ISS uses a system called the Carbon Dioxide Removal Assembly. It scrubs CO2 from the air using chemical reactions and molecular sieves. The captured CO2 then gets processed by another system called Sabatier, which combines it with hydrogen to create water and methane. That's right, the station recycles the air astronauts breathe out and turns it back into drinking water. The water recovery system is even more impressive. And yes, we're talking about recycling everything. Sweat, urine, humidity from breathing, condensation from equipment. Every single drop of moisture gets captured, filtered, and purified. The system can recover about 93% of all water aboard the station. That means astronauts are literally drinking recycled sweat and urine. But don't be grossed out. The water produced is cleaner than what most Americans drink at home. It goes through multiple filtration stages, including activated carbon filters and high-temperature catalytic oxidation. These life support systems alone cost millions to operate daily. The electricity required is enormous. The replacement parts are incredibly expensive. Chemical filters need constant replacement. Pumps wear out, sensors fail, and when something breaks 250 miles above Earth, you can't just call a repairman. If you have deep respect for the engineers who keep these systems running, type respect in the comments below. The Environmental Control and Life Support System, or ECLSS, is the most critical system on the station. It maintains cabin pressure, controls temperature, removes contaminants from the air, and manages humidity levels. Every function requires power, monitoring, and maintenance. Temperature control alone is a massive challenge. In space, there's no air to carry heat away. When the station faces the sun, temperatures reach 250 degrees Fahrenheit. In the shadows, they plummet to minus 250 degrees. That's a 500-degree temperature swing every 90 minutes as the station orbits Earth. Massive radiators extend from the station to dump excess heat into space. Ammonia flows through these radiators, carrying heat away from the cabin. The system uses 1,700 pounds of ammonia circulating through miles of tubing. Pumps push this toxic coolant through the system continuously. When these pumps fail, and they do fail, astronauts have to conduct emergency spacewalks to replace them. These aren't scheduled maintenance walks. These are life or death repairs, where astronauts work in spacesuits while the station's temperature climbs toward dangerous levels. The ISS runs on solar power. 8 massive solar array wings stretch out from the main structure. Each wing measures 115 feet long by 38 feet wide. Together, they generate about 120 kilowatts of electricity. That's enough to power 40 average American homes. But the ISS isn't an average home. It's a laboratory, life support system, communication hub, and living quarters all in one. Every system demands power constantly. These solar panels aren't cheap. Each array costs tens of millions of dollars to manufacture and launch. They degrade over time from radiation exposure and micrometeorite impacts. The harsh environment of space slowly destroys them. Efficiency drops year after year. The panels need constant adjustment to track the sun as the station orbits Earth. Massive rotary joints called solar alpha rotary joints keep the arrays pointed at the sun. These joints are engineering marvels, but they're also maintenance nightmares. In 2007, one of these joints started producing metal shavings and grinding noises. The problem was so severe it threatened to destroy the joint completely. Astronauts had to conduct multiple spacewalks to clean, lubricate, and repair the mechanism. The repair process took months and cost millions. The panels only generate power when facing the sun. During the 45 minutes of darkness each orbit, the station runs on batteries. Originally, the ISS used nickel-hydrogen batteries. Each battery weighed 375 pounds and cost hundreds of thousands of dollars. These batteries had to be replaced regularly. Spacewalks to swap out batteries were some of the most physically demanding tasks astronauts performed. Handling 375-pound batteries while wearing a bulky spacesuit in microgravity requires incredible strength and precision. Recently, NASA upgraded to lithium-ion batteries. These are lighter, more efficient, and last longer, but each battery still costs over $1 million. The station uses 24 of them. But here's the real kicker. All that electricity has to be managed, distributed, and regulated through incredibly complex systems. Power distribution units, converters, controllers, circuit breakers, hundreds of components that can fail at any moment. The electrical system operates at 160 volts DC. That's enough to kill someone instantly. Astronauts working on electrical repairs face serious danger. One wrong move, one short circuit, and they could be electrocuted or start a fire. When a power system fails, astronauts have minutes to respond. Loss of power means loss of life support, loss of heating, loss of communication. The stakes couldn't be higher. Maintaining these power systems accounts for a massive chunk of that $8 million daily cost. The monitoring alone requires teams of engineers on Earth watching telemetry data 24/7. Any anomaly triggers immediate investigation. Feeding 6 people in space for months at a time requires logistics that would blow your mind. Every ounce of food has to be launched from Earth. Cargo missions cost between $10,000 and $40,000 per pound of payload. A single apple might cost $500 just to get to orbit. A bag of coffee, $2,000. A jar of peanut butter, $3,000. The ISS receives supply missions every few months. Russian Progress spacecraft, SpaceX Dragon capsules, Northrop Grumman Cygnus vehicles. Each mission carries thousands of pounds of food, water, equipment, and experiments. A typical cargo mission costs between $150 million and $300 million. Not all of that is food, but food represents a significant portion of the payload. When you're paying those prices, every meal becomes incredibly expensive. But it's not just about launching food, it's about launching the right food. Food that won't spoil. Food that can be prepared in microgravity. Food that provides proper nutrition for astronauts whose bodies are deteriorating in space. Most meals are freeze-dried or thermostabilized. Astronauts add water and heat them up in a small food warmer. Fresh fruit and vegetables arrive with supply ships, but they're gone within days. After that, it's packaged meals for months. The variety is actually impressive. Beef stew, shrimp cocktail, macaroni and cheese, chicken teriyaki, even pizza. NASA employs food scientists who spend years developing space food that actually tastes good and provides proper nutrition. But taste isn't the only concern. Astronauts lose bone density and muscle mass in microgravity. Their nutrition has to be precisely calculated to minimize these effects. Too little calcium and their bones become brittle. Too few calories and they waste away. Too much sodium and they retain fluid, causing vision problems. Every meal is tracked, every calorie counted, every nutrient measured. Astronauts follow strict dietary guidelines designed by nutritionists who understand the unique challenges of space. The cost of feeding 6 people in space runs into millions of dollars every single month. And that's just the food itself. The packaging, preservation, launch costs, and storage all add to the expense. Here's something most people don't realize. The ISS is constantly breaking down. Systems fail regularly. Pumps stop working. Computers crash. Toilets clog. Yes, even in space, toilets are a problem. In fact, they're one of the biggest problems. When something breaks on Earth, you order a replacement part. On the ISS, that replacement part might be months away on the next cargo mission, if you're lucky, if the part is even available. Astronauts spend huge portions of their time just maintaining the station, replacing filters, swapping out failed components, troubleshooting mysterious problems, running diagnostic tests. They're not just scientists, they're mechanics, electricians, plumbers, and computer technicians. The toilet situation alone is worth mentioning. The ISS has 2 toilets. They cost $19 million each. That's not a typo. $19 million for a toilet. Why so expensive? Because making a toilet work in microgravity is incredibly complex. There's no gravity to make waste fall down. Everything floats. The toilet uses airflow to pull waste away from the body and into collection containers. Solid waste gets compressed and stored. Liquid waste gets processed into drinking water. When these toilets break, and they do break frequently, astronauts have to fix them. Imagine troubleshooting a $19 million toilet while floating in microgravity, dealing with waste that wants to float away. That's a regular Tuesday on the ISS. In 2019, the main toilet on the American side of the station broke down. Astronauts had to use the Russian toilet, which meant crossing to the other side of the station every time nature called. The repair took weeks and required parts from Earth. Before we continue, please take a second to like this video and subscribe to our channel. Over 98% of viewers watch without subscribing, and it costs you nothing but makes a huge difference to us. Spare parts for the ISS cost a fortune. A single pump might cost hundreds of thousands of dollars. A computer module could run into the millions. A replacement valve, $50,000. A new sensor, $100,000. And remember, every ounce has to be launched from Earth at enormous expense. The station also requires regular upgrades. New experiments get installed. Old equipment gets replaced. Systems get modernized. Each upgrade requires planning, training, and execution by astronauts who are already working 12-hour days. Spacewalks are necessary for external repairs and upgrades. Each spacewalk costs approximately $2 million when you factor in the planning, training, equipment, and support required. Astronauts conduct dozens of spacewalks every year. These aren't casual strolls outside. Spacewalks are exhausting, dangerous, and physically demanding. Astronauts work in spacesuits that weigh 280 pounds on Earth. The suits are pressurized, making every movement difficult. Imagine trying to turn a wrench while wearing thick gloves inside a pressurized balloon. Spacewalks typically last 6 to 8 hours. Astronauts can't eat or drink during this time. They wear adult diapers because there's no bathroom break option. By the end, they're completely exhausted, dehydrated, and sore. Operating the ISS isn't just about hardware. It's about the thousands of people on Earth supporting those 6 astronauts in space. Mission Control in Houston operates 24/7. Flight controllers monitor every system, every reading, every potential problem. These aren't minimum wage jobs. These are highly trained engineers and specialists earning 6-figure salaries. At any given moment, dozens of flight controllers are watching the station. Environmental control specialists monitor life support. Power specialists watch electrical systems. Communication specialists maintain contact. Flight directors coordinate everything. These teams work in shifts around the clock. When one team goes home, another takes over. The monitoring never stops. The vigilance never wavers. One missed warning could mean disaster. Then there's the training. Before astronauts launch to the ISS, they train for years. Underwater simulations at the Neutral Buoyancy Laboratory, where astronauts practice spacewalks in a massive pool. Virtual reality simulations of station systems. Classroom instruction on every system aboard the ISS. Russian language training. Physical conditioning. Survival training. This training costs millions per astronaut. The facilities alone represent billions in investment. The Neutral Buoyancy Laboratory is a pool containing 6.2 million gallons of water. Operating and maintaining this facility costs millions annually. The international partnership adds another layer of complexity and cost. The ISS is a collaboration between NASA, Roscosmos, the European Space Agency, the Japanese Space Agency, and the Canadian Space Agency. Coordinating between these agencies requires constant communication, translation services, diplomatic efforts, and shared resources. Every partner contributes funding, modules, and personnel. Meetings happen constantly to coordinate operations, plan missions, and resolve conflicts. NASA's annual ISS budget alone runs about $3 billion. That's $8.2 million per day. Russia contributes roughly $1 billion annually. Europe and Japan add hundreds of millions more. Canada contributes tens of millions. Medical support for astronauts is another massive expense. Doctors monitor their health constantly. Bone density scans, cardiovascular tests, psychological evaluations, blood tests, urine analysis. Space does terrible things to the human body, and preventing permanent damage requires constant vigilance. Astronauts lose bone density at a rate of 1% to 2% per month in space. That's 10 times faster than osteoporosis on Earth. They lose muscle mass despite exercising 2 hours every day. Their vision deteriorates as fluid shifts toward their heads. Their immune systems weaken. Their hearts shrink. Medical teams on Earth track all of this. They adjust exercise routines, modify diets, prescribe medications, and plan interventions. When astronauts return to Earth, they need months of rehabilitation to recover. The ISS can't operate in isolation. It needs constant communication with Earth. The Tracking and Data Relay Satellite System provides near-continuous coverage. Multiple satellites in geosynchronous orbit relay signals between the ISS and ground stations. These satellites cost hundreds of millions of dollars each to build and launch. Operating them requires ground stations around the world, staffed by specialists who ensure the communication links never fail. White Sands, New Mexico, Guam, Australia. Multiple locations provide redundant coverage. When astronauts need to talk to mission control, the signal bounces from the ISS to a relay satellite down to a ground station through fiber optic networks to Houston. The entire system has to work flawlessly because lives depend on it. Video feeds, telemetry data, experiment results, email, phone calls home. All of this flows through the communication network constantly. The bandwidth required is enormous. The reliability has to be perfect. The station transmits gigabytes of data every single day. Telemetry from thousands of sensors, video from multiple cameras, scientific data from hundreds of experiments. All of this has to be received, processed, stored, and analyzed. Communication blackouts are terrifying. When the station passes over areas without coverage, contact is lost for minutes at a time. During these blackouts, astronauts are on their own. If an emergency happens, they have to handle it without ground support. So why spend $8 million a day on the ISS? What do we get for that investment? The research conducted aboard the station has led to breakthroughs in medicine, materials science, and technology. Experiments in microgravity have produced results impossible to achieve on Earth. Drug development benefits enormously from ISS research. Protein crystals grow larger and more perfect in microgravity, allowing scientists to understand disease mechanisms better. This research has contributed to treatments for cancer, muscular dystrophy, and other diseases. One experiment led to a drug called Prolia, which treats osteoporosis. The research conducted in microgravity helps scientists understand bone loss mechanisms. This drug now helps millions of people on Earth. Material science experiments have led to stronger alloys, better manufacturing processes, and new technologies. Combustion experiments in microgravity have improved engine efficiency. Fluid dynamics research has advanced our understanding of how liquids behave. The knowledge gained applies to everything from smartphones to aircraft construction. Manufacturing techniques developed for space have been adapted for Earth-based industries. Earth observation from the ISS provides critical data on climate change, natural disasters, and environmental trends. The view from 250 miles up reveals patterns invisible from the ground. Cameras aboard the station track hurricanes, monitor deforestation, study ocean currents, and document changes in ice coverage. But perhaps the most important benefit is preparing for future space exploration. Everything we learn about keeping humans alive in space applies to future missions to the Moon, Mars, and beyond. The ISS is a testbed for life support systems, radiation protection, psychological challenges, and long-duration spaceflight. Without this research, sending humans to Mars would be impossible. NASA is learning how to grow food in space, how to recycle resources with maximum efficiency, how to maintain mental health during long isolation, how to exercise effectively in microgravity, how to perform surgery in weightlessness. All of this knowledge is essential for future missions. The ISS is teaching us how to become a spacefaring species. Living on the ISS is one of the most dangerous jobs in existence. The risks are constant and deadly. Micrometeorites strike the station regularly. These tiny particles travel at thousands of miles per hour. A piece of debris the size of a paint chip can punch through metal. A marble-sized object could catastrophically damage the station. The station's hull is designed to withstand impacts, but larger debris poses a serious threat. The ISS has been hit thousands of times. Windows have been chipped. Radiators have been punctured. Solar panels have been damaged. Several times, astronauts have had to shelter in place while dangerous debris passed nearby. They retreat to the Soyuz spacecraft, ready to evacuate if the station is hit. These close calls happen multiple times per year. In 2021, debris from a Russian anti-satellite test forced astronauts to shelter for hours. The debris field created thousands of new objects in orbit, all traveling at lethal speeds. Fire is another nightmare scenario. In microgravity, flames behave differently. They form spheres instead of rising upward. Smoke doesn't rise either. It just spreads throughout the cabin, making it impossible to see or breathe. The ISS has had fires, small ones thankfully, but any fire in space is terrifying. There's nowhere to go. You can't open a window. You can't evacuate outside. You have to fight the fire or die. Fire suppression systems aboard the station include special extinguishers and breathing masks. Astronauts train extensively on fighting fires. They practice until the procedures are automatic. Ammonia leaks are another deadly threat. The station's cooling system uses ammonia, which is toxic to humans. A leak could contaminate the entire station within minutes. Astronauts would have to evacuate to the Russian segment and seal off the contaminated areas. In 2013, an ammonia leak during a spacewalk nearly killed an astronaut. Water started filling his helmet, threatening to drown him. He made it back inside with minutes to spare. The investigation revealed a contaminated filter had caused the leak. Rapid decompression is the ultimate nightmare. A large hole in the hull would cause the station's air to rush out into space. Astronauts would have seconds to reach safety before losing consciousness. The station is divided into modules with hatches that can be sealed. If one module loses pressure, astronauts can seal it off and retreat to other areas. But finding and patching a leak while the air is rushing out requires incredible calm under pressure. Astronauts train extensively for emergencies. They practice evacuating to the Soyuz spacecraft that serves as a lifeboat. They drill on fighting fires, handling toxic leaks, and dealing with rapid decompression. Every day in space is a day where something could go catastrophically wrong. The $8 million daily cost includes all the systems, procedures, and people dedicated to preventing disasters. The International Space Station costs $8 million daily because keeping humans alive in the most hostile environment imaginable requires constant vigilance, cutting-edge technology, and thousands of dedicated professionals. Every system, every backup, every procedure exists because without them, astronauts would die. That price represents humanity's refusal to accept limits.